Hi, Georgia. Can you share your screen?
Hello, can you hear me?
We can hear you. Can you share your screen?
Yes, let me do that.
Okay. And,
Γιούλη, καλησπέρα. Δεν σε βλέπουμε.
αυτό θα ήταν το επόμενο.
Τώρα διορθώθηκε. So can you see me now?
Ναι, σε βλέπουμε.
Okay, I cannot see you since I'm sharing the screen.
Okay.
Okay.
Καλά, θα
Hi.
μας δεις μετά. Δεν αλλάξαμε, ήδη είμαστε.
Καλό είναι αυτό.
Τα λέμε.
Τι γίνεται, πώς πάει?
Μια χαρά. Με ακούτε καλά, γιατί εγώ σας ακούω λίγο με διακοπές.
Με διακοπές.
Ναι, αλλά αν με ακούτε εσείς καλά είναι ok.
Επίσης ακούω μια χαρά.
Αυτό.
Μιλάνε από πίσω, ίσως αυτό ζορίζει τα πράγματα. Ακόμα δεν ξεκινήσαμε. Κάτσε να τους πω ότι ξεκινάμε.
Εντάξει, όποτε είστε έτοιμοι, δεν βιάζομαι.
Okay, we're starting in 1 minute. Okay, we're starting in 1 minute. If you have food, you need to be inside. Everybody, can we start? Okay. All right, let's get started. Welcome, everybody. This is our March, I guess, Computer Science Colloquium. We're very happy to have with us today, remotely, but still with us today, Dr. Georgia Koutrika, who's a research director at the Athena Research Center in Greece. Before that, she was a senior research scientist at HP Labs, also a researcher at the IBM Almaden, and before that, a postdoc at Stanford. I know Georgia probably over 20 years. I don't remember the exact date. Some this has been a long time. So her research is at the intersection of data management and deep learning, focusing on conversational data exploration, fair and ethical algorithmic systems, and learned data management. She has, a great publication record, patents. She's been very active also in various leadership roles with the data management community, including being a member of the LDB Endowment Board of Trustees. A lot of other stuff that are very valuable to the community, and also show here standing in the high standing in the community, data management community. So with that, let me, instead of listing all the awards, let me just pass on the microphone to Georgia, who's going to talk to us today about unlocking data with words, epic journey of natural language interfaces. Georgia, you have the floor.
I have the floor. Hello, everyone. It is good to be remotely with you. Maybe next time we will do it. We'll be in the same room. So I will just focus on the presentation. So I will not be able to see the room anymore. So if you have any questions, maybe we can take them at the end, or just shout out so that I can hear you and interrupt the talk. Okay. So let's get rid of that. Okay, so today in the next, let's say 45 minutes or 50 minutes or so, we're going to talk about a topic that is very close to my heart, but it is also very, very hot these days. And we're going to talk about natural language interfaces for databases. So let me also get rid of that, I hope. I'm not sure how to do this. Okay. We will have to stay with that. Okay, so I will not say anything more about myself, because Alex already gave a long introduction, and thank you so much for all the information you shared. I just want to say that my team and myself are working on 3 big topics that are interrelated, and these are conversational data exploration, learned data management, and fair recommender systems. And all this can be seen in the intersection of data management and deep learning that we are working on. So let's start, however, our trip, and I will go back in time in around the 1970s, where the father of relational databases, code, at this time was working at IBM. And he was already not only talking about relational databases and SQL, but he was already talking about the need for systems to support users to access data using natural language. So he had designed a system that was called Rendezvous, and the Rendezvous allowed the user to ask his query using natural language. For example, give me the list of the parts of the suppliers of Houston parts. The system would ask clarifications back to the user, again in natural language. And when this dialogue reached a good result, then the system would show the results to the user. But in reality, even until these days, what we are using are either form-based interfaces, like the one that you see here that is used by the European Union for access information about all the data and all the proposals and the projects that are running under the European Union framework. But as you can see, form-based interfaces are simple to use on one hand. On the other hand, they offer limited query and exploration capabilities. The other extreme, the other option, if you like, is to go down closer to the system, use a query language like SQL or a programming language like Python, and formulate exactly what you are looking for, add the computations that you want, and so forth. But this comes with different cost. That assumes that you know exactly how your data is stored, the data schema. You know exactly what you're looking for, so that you write exactly the code that needs to compute and return the desired result. And also you are a programmer, either for SQL, Python, or in a different query language. So this is not enough. This is actually very limiting. What we would like to have is the ability to express whatever computation or information access request we have using the language we know best as humans, which is a natural language, English, Greek, Chinese, whatever we're used to speak. For example, if we are an astrophysicist, and we have worked with astrophysicists exactly for this purpose, they want to access data to find interesting information. For example, find all photometrically observable galaxies. Okay, they want to ask this. They don't want to say that in SQL or any different language. Or a tourist organization wants to access information related to meteorological data. So a question that they would like to ask is, what is the average rain over Athens in summertime for the last 2 years, so that they prepare a travel package for vacation. and so many other examples with biological data, with scholarly data. Name your data and name the questions that you would like to ask. So what we're going to do, we're going to take a trip, and we will build a natural language interface, and we are going to start with the challenges first of all, okay? So I want you to understand that a natural language comes with inherent challenges that we need to address. One of those is the ambiguity. For example, when we say show information about Paris, do we refer to Paris, the city, to Paris as a person? When we say are Brand and Angelina married, do we mean to each other or do we mean to someone else? There are different types of ambiguity, and the problem they create is that they can have a simple question can have multiple query interpretations. That affects the system efficiency because it takes the system more time to make the right computations and to try to decipher the query. And also it has it affects the system accuracy because the system needs to figure out what the user may mean, and that of course may not be it may not find the perfect answer. The second challenge I would like to mention is paraphrasing. We may say the same thing in many different ways. For example, how many people live in Naples versus what is the population of Naples. The problem that is created is that semantically equivalent queries may not be answered in the same way. And in some cases, they may not be answered at all. For example, the population may be a column in our database, so the system may be able to find that very easily. But on the other hand, how many people live may be more difficult for the system to compute automatically, to translate automatically. And of course, there are more challenges. We're not going to go through all of them, like when there is information missing but inferred from the query. For example, who was president before Obama? So here we mean president of the USA. Or user mistakes that complicate things even more. For example, spelling errors, syntactical errors, and so forth. So we are going to split the different systems in three big eras or generations, if you like. And the reason we are doing this, and we start from the early systems in 1960 to 1990, is that we're going to see, first of all, how the systems evolved through the years, but at the same time, how they share and they have in common the principles, design principles that we see even these days. We're also going to see the advantages and the disadvantages of the different options. And hopefully by the end of the talk, we will be able to think about how we can combine, if you like, the best of all the options that we have seen. So let's start with the early systems. So the very early systems used, of course, patterns like the one that we see here, where the pattern would say, if you see the word capital and then followed by a country, then the action you need to take as a system is to report the capital of the row, where country is equal to the country specified in the query. So this type of pattern matching systems were, of course, very simple to build, but also very primitive. And as we know, patterns can easily break. So it was very easy that the question would contain something there that the system would get confused immediately. Now, as an answer to these problems, the next category of systems in this generation, this era, divides the problem into two parts. They say, okay, first we need to have a way to understand the syntax of the natural language question. Okay, and with that, we're going to build a parse tree that tells us how the different query tokens, the different query keywords are related to each other. And then we take this parse tree and we have specific rules that build the executable query. For example, this would be a syntax from a system called Lunar that was a data management system that allowed access and information related to lunar rocks, moon rocks. So you can see that the syntax is very primitive. It says how, what type of questions I can have, what type of words I can use in these questions, and so forth. And the syntax tree that would be built for a specific query would look like this. Then, based on the specific mapping rules that we have, that would be an example of a query that is generated for this system. Now, what we observe here is that this type of systems interfaced application-specific database systems, and of course, we don't see SQL at all in this case. Now, the next generation of systems has the following idea. Okay, instead of trying to understand the syntax, I want to try to understand the semantics of the query. So here, essentially, we take the NL question and we try to generate a tree that captures the concepts and the relationships of these concepts inside the query. And then we follow the same logic, having a query mapping a module that uses specific rules again to generate an executable query. Of course, as we can understand, these semantic grammars contain hardwired domain knowledge, and of course, they cannot be transferred to other domains. And the latter was one of the systems that was used in the Navy at this point in time. Now, all these systems evolved to what we see here that has three parts. We have one part to understand the syntax, one part to understand the semantics through the semantic interpreter, and then, of course, we have again the query mapper. For example, for a query like the one that we see here, what is the capital of the countries bordering with Greece? The parser would generate a tree, and then if we go to the semantic interpreter, we would see either information like rules, like capital and country, or they would use some type of ontology, or they would use some type of a lexicon to provide semantics and interpretation of the concepts that we have in the tree. Then the semantic interpreter would generate a logical query that would capture these concepts and their relationship. So we don't generate the executable query in one step, but we have this logical query that is fed to the query mapper, and now we see that we generate SQL queries. So these systems now are quite mature, if you like, and they can generate SQL queries. And the novelty that they have added, as we have seen, is that they separate the linguistic front from the underlying DBMS, offering this independence that helps the system to be used with different databases, with different domains. Now, in summary, in this first generation of early systems, what we see is that initially the syntax and the semantics rules were based on very simple ideas. Then we see that these ideas start to evolve, and more recent systems, they follow a representation-based approach, as we saw in the previous slide, where essentially we use a logical intermediate representation, and we don't translate immediately to SQL. And they also start adopting advances from the NLP field. However, we have to say that still these systems were experimental. And even at the IBM, when Code was building his own system, Rendezvous, that was also experimental. It was never really adopted by IBM. But we do see a few industrial products as well. One maybe of the most popular at that time was Microsoft SQL Server English query that was launched around the end of around 1990, 1992. But then it was also abandoned because these systems were too early for, for their time, if you like. And now let's move to the second generation, a little closer to our times. And we're going to see approaches that follow what we call the database way. And we're going to see why we say that. So these approaches tackle the problem of translating a natural language question to SQL as a database mapping problem, where the goal is to map query terms to database elements, tables, columns, and values, and then find the desired interconnections of these elements that would capture what the user is looking for. Now, the first system that introduced this idea was discovered that introduced the idea of having query interpretations as subgraphs over the database schema graph. And we see different names for that, joining networks, joining tuple networks, and so forth. But let's focus on the example here to see what we mean. So we have a query like dramas by Woody Allen. So the first step would be to map these terms using indexes to the underlying database elements. So here we see dramas goes to the genre attribute of the genre table, and Woody Allen, of course, is the name of the director. Then the next step would be to try to traverse the graph to find how these relations can be joined together. And usually these systems tackle this problem as finding the minimum Steiner tree. Now, a lot of systems in this period of time have adopted this concept of seeing query interpretations as subgraphs, and but we also see different variations. And one that I would like to mention is the one called the logical subset, where the idea is that the answer to a query does not only have tuples that match directly to what the query says, but also results that transitively join to these tuples. Okay, what does it mean? Let's again see an example. I'm asking, tell me about Woody Allen. So a possible answer would be, as a director, Woody Allen has directed Match Point and Melinda, and so forth. Okay, so we see that we generate a little snippet of information about Woody Allen. So how do we do this? So let's return to our database example here. And again, the first step would be to map the terms using indexes. So here we have mapped Woody Allen, of course, to the director name, but then the next step would be to traverse the graph to expand to other relations that would contain useful information that would help us understand better who Woody Allen is. Now, how do we traverse the graph? We have different constraints, like constraints based on the number of relations, based on the significance of the joins between the relations, and so forth. Then the third step would be to populate the relations with tuples and joining tuples, again with constraints, because we want to have a logical subset that has a meaningful size. And then this particular work, what they also did was to generate a natural language explanation, description of the result, like the one that we see here. So that was also a different idea. Okay, then Nalir comes in, and it brings a revolution, because it says, hold on, we're not just dealing with a database mapping problem. We are also dealing with a linguistic problem. So we need also to understand what the query is saying. So what they propose is to take the syntactic parse tree, and they use the Stanford parser at this point to generate this syntactic tree. And then the second thing they would do, they would take all the nodes of the tree and all the words of the natural language question and try to find what they mean, how they would map either to operations like return would be mapped to select, or to database elements like author or paper maps to publication, or to other operations like the greater than and so forth. Once they did that, then they would restructure the parse tree in order to come up with what they call the valid parse tree, which an easy way to understand this would be how if we had expressed our query in a very good way, the parse tree would look like the one that we see here. So ideally, we would like the author to have said, the user to have said, return the authors, where the papers of the author in NLIDB after 2000 are more than Bob's. And then they did one more transformation to generate what they call the query tree. And now the query tree still contains concepts and as they are mapped in the underlying database, but it also has the logic of how to combine this in order to generate the result. And they would take this and then based on that, they would generate the required SQL code to return the results for this query. And we're going to see an example for that a little bit in a few minutes. So, but I would like to mention a few important things that these systems have brought. One of those is query disambiguation. So terms in a query may map to more than one database element. And that, of course, means that also we may have multiple interpretations for a query, different operators, different orders of operators, and so forth. For example, this simple query that looks for Italian restaurants, and the schema that we see here comes from the Yelp database. And we can have several possible term mappings, which also generate several possible query interpretations, but not all of them are meaningful. For example, a business that is categorized as restaurant and as Italian is actually a good one, but a business categorized as Italian whose address contains restaurant is not a good one. But it happens that restaurant also exists in the address of some restaurant. Now, the second, what they did for query disambiguation was either to try to make sense from the joining tree, for example, based on the size of the joining tree, bigger trees would be less important, or based on the edges of the tree. Some systems use information retrieval heuristics that would try to understand the importance of the terms and their position inside the database to figure out which interpretation would be more important. And then other heuristics, for example, NLIDB would try to see how the parse tree would look like, what would be the similarity between the initial parse tree and the query tree they built after all the transformations and so forth. Now, the other thing that we want to mention here is that all these systems build executable code, and they also try to optimize it in order to return results to the user in a more efficient way. And we see different approaches here. For example, Discover was trying to build an execution plan that would minimize the number of computations by caching results that would be reused later. We see generating top-K results without materializing all possible joining trees. We see NLIDB's approach where it builds blocks of queries, trying to bring results in a more efficient way, and so forth. But again, execution and efficiency of execution was something very, very important. Now, how do the systems look? At a high level, we have these 4 parts, okay? So the parser would try to understand the natural language query. And in simple systems, it would just tokenize, or it would just take the n-grams of the query. In systems like NLIDB, it would try to generate a dependency parse tree that would capture the syntactic relationships between the words in the sentence. Then we have the entity mapper. So the entity mapper now maps the query elements to database elements and also to commands, to operations in SQL. And this is something important here that this is, if you like, a big difference compared to the systems of the earlier years where the mapping was happening as the very last step. Here in these systems, mapping is a very important step, and it happens right at the beginning because we want to make sure that we are building a query that is semantically correct. Okay? Then the interpretation generator tries to figure out the dependencies between terms and phrases and map them to joins, to operations, and also determine the order of operations. And we see here different types of interpretations, as we have seen: joining trees, query trees. Athena, that was a prototype system from IBM that was also productized, was using their own ontology query language to generate the results. And finally, we have the SQL translator and executor that would generate the final query. And let's run a simple example, okay? So we have the query, what movies have the same director as Revolutionary Road? Then the parser would generate a syntactic tree like this one. Then the entity mapper would try to map a movie, Revolutionary Road, and so forth to the underlying database elements. The interpretation generator would figure out how these elements should be combined in order to generate the answer of the query. And then the final result, the final SQL query would be as we see here. Essentially, we run the execution flow of Nalir. And as you can see here, Nalir for this query would generate 3 different blocks that when executed would return the desired result for this query. Now, what do we want to remember from these systems? That database mapping is central here, and it comes very early in the whole process to ensure semantic correctness. These systems allow for multiple query interpretations, and they rank them also. They generate code that is always executable over the database, and they really care about efficiency, the query response time. Okay, that's why we say database approaches. These are elements that are important for these systems. Now, as we're going to move to most recent deep learning neural systems, all these 4 characteristics, we are going to start forgetting them, okay? And this is an important distinction between these systems and neural approaches that we're going to see now, okay? So, but before we go there, I want to mention also a couple of things that are important. First of all, evaluation. Okay, these database systems would not use common benchmarks or very large data sets or query sets. We would see different approaches, like some of them would use a user study, another system would do a manual evaluation. They would use different or proprietary data sets like TPCH or DBLP and so forth. Now, of course, we understand that in this way, we would not have a good understanding of the capabilities of the different systems. So we build a benchmark that we called Thor that contained keyword queries, but also natural language queries, and it was divided into 17 different categories. These categories match to different SQL challenges, like having joins or no joins, aggregates, nested queries, and so forth, and also some important NL challenges. Okay, and these queries span 3 different data sets. Now we compared all the previous systems using this benchmark, and we found very interesting observations. The ones that I would like to share with you today is that, first of all, there were no universal solutions. So different systems would be good for different challenges, but also different data sets would present different challenges. So you see here at the bottom left side of the slide that we have the 3 data sets. We see 7 of the challenges that we have, and you see how in the different systems these challenges are either more difficult or easier, so we see totally different behavior. Okay, and let's now dive into, well, the last few years and the deep learning era that changed things quite a lot. And just to get an idea of how things are running fast these days in this area, if you Google, if you go to DBLP and you search for natural language interfaces or natural language queries, okay, that would be what you would see. So we would see that, okay, yes, of course, there are some very early works already from the 1970s, okay, and that goes until today. And if you count all these works, it will be something around 600 for the first case and around again 600 for the second case. But then if you type text to SQL, okay, up until last year, in the last 4 or 5 years, it will be already over 300 references. And these go fast, these go exponentially at this point. And the reason is that the text to SQL term became popular thanks to the neural approaches for this problem, where essentially they formulate the NL to SQL problem as a language translation problem, where the purpose is to train a neural network on a large amount of natural language query and SQL pairs. Okay, so if we take a look at the text to SQL datasets, we have 2 benchmarks that appeared, WikiSQL and Spider, that essentially made possible training neural systems for the text to SQL problem. Before that, we would see, small data sets that were not, of course, appropriate for training or even evaluating systems. And what we see now as we come forward is that more benchmarks have been proposed. Not all of them are so widely adopted like WikiSQL and Spider. These days, BERT is one of the most popular because it has more complex queries and more complex databases compared to what the Spider had and also to what the WikiSQL had. Now, if we want to draw a timeline of deep learning text to SQL systems, and here we don't show all systems or all the advancements, but what I want to show here is how big milestones in NLP and big milestones in benchmarks have changed how this timeline looks. So the appearance of the 2 large data sets, WikiSQL and Spider, essentially triggered all these systems the appearance of all these systems that we see. And then as we go forward, we see that systems start to get more complex and more powerful and use a large variety of techniques. Then pre-trained language models become popular, and they are also adapted by many of these systems that they change their whole logic of how they see the text to SQL problem. And even more recently, we have large language models, and we have systems that either completely rely on these systems or they are PLMs themselves, and they have a lot of power, as we are going to see, but they also carry some of the drawbacks of these systems, and we are going to touch upon this as well during the rest of the talk. Now, a high-level neural architecture for the text to SQL problem would look something like this. And I would like to focus first of all at the core of this architecture, which is the encoder-decoder. Now, the goal of the encoder is to read its input and transform it into internal representation. And at the same time, it tries to infuse a representation with information that comes from the different inputs. And that is a mechanism that is called neural attention. Now, the decoder now is responsible for making predictions about the most probable SQL query or SQL parts of a query. But let's take things from the start, okay? And let's start with schema linking. Now, schema linking is a problem of discovering mentions of database elements in the user query. And we have to say that this step is optional. Not all of the systems have it. In fact, most of the systems say that, you know, the encoder decoder can magically find these mappings. But we're going to see how that works, okay? So what type of schema links we are talking about? We're talking about finding links to tables, finding links to columns, and to values, okay? And here in the question that we see, one possible table link is the one that we see here, and we also see a possible value link, not necessarily correct, however, just a possible interpretation. Now, one problem is which parts of the NL query to consider. N-grams, named entities, just tokens. We have seen different approaches here. How do we decide on a match? Again, we have seen here different approaches, from exact and partial matching, which is the simplest one, to classifiers that try to understand, for example, 56, what does it mean? Probably it is the age of a person, for example, okay? Now, having done this, the next step in this process is the natural language representation. Remember that a neural network does not understand strings. So we need to take the input, which is the natural language question. It may be the database schema, and optionally the schema links if we have a schema linking step, and we transform them into a numerical representation. And here we have different options. For example, word embeddings, that was the go-to option in the early systems. But then when pre-trained language models like BERT and T5 appeared, these were adopted, and they achieved big differences in the accuracy of the systems. Even the same architecture, and we're going to see an example a little bit later, the same system switching from word embeddings from GLOVE to BERT achieved an increase in accuracy of 10%, which is important with this just simple change. Now, what about input encoding? Okay, how do we select the encoder? And more importantly, what we want to discuss today is how we structure the inputs. What options do we have here? Some early systems would use one encoder for the query and one encoder for the schema. Then most recent systems and essentially systems that use PLMs and LLMs would go with one common encoder that would combine the query and the schema in a single input. We have also seen graph encoders, where essentially here they try to capture the fact that we have a schema, we have tables that are connected to each other, columns that are connected to the tables, and the query tokens that are connected to these elements. And it would be nice to capture this information. The problem with this approach is that it cannot be used with off-the-shelf PLMs. It needs its own encoder, and that's why it was not. We have not seen too many systems adopting this approach. Now let's move to the output decoder, and here essentially we are going to see how it builds the SQL, the desired SQL. Okay. So the first systems would use a sequence-to-sequence approach. We have one sequence that is our natural language question, and we're going to generate another sequence that is our SQL query. Okay, and the first systems were following this approach, but they realized that although it is simple and it works very well with off-the-shelf models, nothing prevents the system from generating queries that contain errors because, you know, I'm just seeing a sequence of tokens. I can insert in this sequence things that will not make an executable query or mention database elements that do not exist. Okay, so that's why it was abandoned. But then, as we're going to see, most recent systems are actually using this approach again. Okay, now as an answer to the sequence-to-sequence approach that we saw earlier, a stage-based approach appeared that said, okay, instead of trying to spit out the SQL query at once, we're going to use a template of what an SQL query means for us, like the one that we see here. And then we will have slots, and different neural networks will try to, or classifiers, will try to predict what goes inside each slot. Okay. Now, of course, divide and conquer is always a nice approach, but the problem is that this approach does not scale. You want to have different types of queries or more complex queries. You need to have all the different possible templates or sketches for this type of queries. And that is not exactly very easy to generalize in this way. Now, the third approach is a grammar-based approach. That reminds us already the early systems that they used an intermediate approach. So we see how, you know, history and approaches repeat, but of course here they are more sophisticated. So here we're using a grammar, and the decoder generates a sequence of rules. And then this sequence of rules would be read by the system, and they would generate the final SQL query. And we see many important systems in this using this approach, and we're going to see one of those today as well. Okay, so the good with the grammar is, of course, that it guarantees the correctness of SQL query compared to sequence-to-sequence approaches. But of course, it has, the requirement that you have to design your own decoder that will abide to your grammar and to the syntax that you want to use. Okay. And now the final step is output refinement, which again, this one is maybe optional. Okay. So we're talking about neural networks. So nothing tells us that whatever the network comes up with, it will be an SQL query that executes. Except if you have, of course, a grammar-based approach that is more, you are more confident there. So an output refinement step, and we have different choices here, make sure that the SQL query executes. One of those approaches is what they call execution-guided decoding, where essentially it executes partially complete SQL queries and rejects the ones that will not, that contain errors or yield empty results. Of course, we already understand that this creates overhead, but neural people do not always, care about these type of things. Now, I would like to go through some key systems that they have introduced important developments in this area. And I would like, of course, to start with the first one, that was the Sec2SQL, that used that was a sequence-to-sequence translation system. What we see here is that it would use a separate encoder for the query, a separate encoder for the table, okay? And it would also use, it would also use one classifier to find the aggregation function, one classifier to find the column, and for the where clause was the sequence-to-sequence translation, okay? Now, they also had the idea of using reinforcement learning at this point in time, okay? but it didn't generate the results, the accuracy that they were looking for. And that's why SQLnet appeared, and SQLnet also, they introduced the WikiSQL benchmark. SQLnet brought the idea of using sketches. And they also brought the idea of using column attention. Of course, now more recent developments like transformers, they have a more advanced notion of neural attention. But SQLnet was in fact the first one that introduced a neural module in each of the network that tried to emphasize words in the natural language question that could be related to database elements. Okay, they also introduced the idea of using glove embedding, so they were also advanced in that sense. The big problem that this approach had was that, and we had implemented the SQLnet at that point in time. The neural networks were extremely big because for each slot in the sketch, the slot required its own network. Okay, and that was not, of course, something that would scale very nicely. Now, the next one that I want to mention is IRNet. IRNet was the system that introduced the idea of schema linking, which we know from, of course, from the previous database approaches, but IRNet brings that into neural approaches. And they say that, the neural network is good for generating text, but we need to also to consider that we have a database mapping problem. Okay, so what these guys did was the following. First of all, they would split the query into n-grams. And then if an n-gram matched a column or a table in the database, either as an exact match or as a partial match, then they would mark it so. Then the second rule they had was that if an n-gram was inside quotes, then it would be considered as a value link. And they would not access the database at all, but they would just consult ConceptNet to understand what type of link what type of value link we have. For example, for New York that we see in the query, they would consult ConceptNet, and ConceptNet would say, oh, this is a state. Now, once they did it, they would split the NL question into parts, into spans, based on the type of the discovered links. Okay, and then we go to the encoder, and what happens here is that, first of all, the schema links would append it next to the related NL query parts. So you see here for department, that would go with table. For New York, that would go with a value. They would use BERT as the encoder, and then at the output of BERT, if there were spans like the one that we see here that required more than one token, they would combine it into one token, and they would also combine column tokens with a type appending, like the one that we see here, to emphasize the type of the particular column. And the last part was the decoding, where they also had here a new idea to use a grammar-based approach, and they introduced a language called SemQL. So the system would generate rules in SemQL as an abstract syntax tree, and then these rules would be used by the system to generate the final SQL query. So IRNet brought a lot of new contributions in the field. Now we're switching gears, and we're going to REST the SQL that has the following very nice ideas. The first one is that it has one step, the top part that we see here, the cross encoder, that takes as input the query and the whole database schema, and in its output, it generates only the schema that is, keeps only the schema that is related to the query. Then the second and very nice idea is that then they use a sequence-to-sequence decoder. And this decoder does not generate just the SQL query. First, it tries to generate the SQL skeleton for the query, and then followed by the SQL query. And this nice idea gave them a very nice boost in performance, this combination of the two ideas. Now, we cannot, of course, not mention Picard and T5. So T5 transformers essentially they introduced a very nice idea that you can pre-train your system on very basic tasks like masking parts of the text, and then the network will try to guess the missing parts, and then you could fine-tune this for different tasks, and the system could do like from machine translation to classification to question answering. Well, why not translate from NL to SQL, which they did. But now this particular text to SQL system, they also introduced Picard, where Picard tries to stop the generation, the autoregressive decoder from generating outputs that either contain grammar or syntax error, or they contain attributes that do not exist. Let's see an example, okay? So it starts always with spitting out the from, and then the next tokens. From this next token, select is of course wrong, incorrect syntax, so it is dropped. Then it expands the remaining ones, and we see that after stores age is not the correct one, so it would drop it as well, and so forth. Okay. Graphics T5 is one of the systems that use the idea of having the input structured as a graph. And as you can see here, they modified the T5 encoder and they added graphics layers to encode the graph information for the text to SQL problem. And well, we could not all forget to mention DinSQL that uses GPT-4 and uses prompting techniques, and in order to answer the text to SQL problem using few-shot learning. So I decompose the task into four subtasks. First, to do the schema linking, then to predict the query skeleton, then to do SQL generator, and then it also prompts once more the network to self-correct itself, okay? And that is also a very nice approach. And lately, prompting techniques for text to SQL systems have become extremely common. Well, in summary, these neural approaches see the problem as a neural machine translation problem. However, the focus is solely on translation accuracy. They don't care about efficiency, which we have seen it is an important requirement as well. And they are also very expensive. So I would like to, at this point, remind us that we're not dealing just with the translation problem. We're translating to SQL, and SQL also has challenges. First of all, it has a strict grammar, limited expressivity. There are different ways to write a SQL query. Some may be more efficient than others. Then the database structure also poses specific limitations. The user data model may not match the database schema. The same query, like the example that we see here, okay? Find directors who released the movie this year. Over one database, it may need a few joins. Over a different database schema, it may need no joins at all, okay? So it is not, the system may have to translate the same natural language question differently over different databases. Unfortunately, neural approaches ignore these particularities, and this is something that we need to have in mind, Okay, so if we put side by side the database approaches and the neural machine translation approach, we see that they are somehow complementary. So on one way, the database approach is generated always executable code, grounded solution, and they also tackle query ambiguity. But of course, they struggle with more complex and diverse natural language expressions, and also with challenges like paraphrases, mistakes, and so forth. Now, if we go to the neural machine translation side, of course, dealing with NL is much easier, but we do depend on having training data. We cannot cope with unseen data or unseen queries. And we also we need to remind ourselves that they are energy consuming models, at least most of them. So we think that natural language database interfaces should combine the best of both worlds. And closing this talk, I would like to pinpoint a few more challenges and to open the floor for discussion. One big challenge has to do with query answerability. Okay, how can we tell if a natural language question can be answered or not? Okay, when we're dealing with SQL queries, the system knows exactly whether they can answer the query or not, because it will check for syntactic correctness and it will also check for semantic correctness. What about an NL question? Ideally would say, okay, does the NL question map to SQL that captures the query intent? Is the SQL executable over the underlying database? Yes, but how do we really capture this? It is hard to define a set of comprehensive rules or checks to make this explicit, and it is also hard to answer them successfully. Okay, so for example, a system may fail to recognize that the question is answerable due to ambiguity, due to different vocabulary. Okay, it may also fail to recognize that the question is unanswerable. In fact, all of the systems will try to generate an SQL from an NL, even if the NL says things like calculations that are not in SQL, expressed in SQL, or that it is out of scope because the user asks for a chart, or smoke talk, or asking opinion. So very recently, there have been focused works that try to understand which queries cannot be answered and stop the system from trying to answer them. Okay. Query coverage. Now, we actually have a paper in EDPT in 1 week from now, where we took all the existing benchmarks and we were trying. One of the goals of this experimental study was to try to understand what these benchmarks really tell us. Okay, when we evaluate a system using one of those. And I have an example here with Spider, which is the most popular, still followed by BERT, as we said. And you can see here the queries, the type of queries that are covered by this system. So most of the queries are simple select from where queries. Okay, so when we say that, oh, I have a system that has an accuracy of 80% over this type of queries. Okay. Other important conclusions came from this study, but I would like to continue on the next and final challenge, I believe, real world data. Okay, it is good when we're talking about Spider and BERT. They have simple databases, small databases, but in reality, the data that we're dealing with have very cryptic schemas. As you can see here, U, G, and spec ops are attributes from a big astrophysics database. Our schemas are extremely large. Only one table can have like 500 attributes. We don't have training data, and none of these systems actually work. So what do we do? So one of the things we did was, first of all, to build a science benchmark, which is a benchmark on 3 real-world and highly domain-specific databases. And we also built a data augmentation approach that tries to go into the database and auto-generate training data from scratch. So I will pass this. I would like, of course, as a database person that wears a deep learning hat, I would like to finish with the comment that it is good to have systems that translate from NL to SQL, but they should also do this as efficiently as possible. Now, the natural language interfaces have been the holy grail of the database community for over 50 years. And initially, the first efforts ended up with frustrated users. But now the landscape has changed. So users are more accustomed to working with such interfaces. Also, the technologies that we have become very powerful. So we expect that in a few years, the way we interact with data will be probably much more different than we know nowadays. And with this, I would like to finish the talk. I know that I'm a little over time, hope not extremely over time.
Let's thank the speaker. So we have time for a couple of questions.
I had a question. This was very interesting to me. One of the things, can you hear me?
Yes.
One of the things that you talked about was the inaccuracy, right? So when you translate natural language to SQL queries, but there is also the inherent SQL inaccuracies, right? That the previous approaches, which one gets closer? Does use LLM to translate into SQL versus the approaches before 2017? Which one of them gets more accuracy?
The earlier approaches get closer to, they actually always generate executable code that is, syntactically and semantically correct. With LLMs, this is not their first goal, if you like. So that's why in the systems that we currently build, we try to combine what the first approaches offer us with, of course, the extreme capabilities of LLMs to understand the natural language and to generate a text.
Is there, I guess, an advantage? Like, did you ever experiment with the different types of autoencoders for the query? Like, for example, did you find that autoencoders that use, for example, charactograms versus tokens perform better or worse?
I cannot hear you very well. I think
Can you come closer?
if you come closer, I will be able to understand. Yeah, thank you.
So my
And I can also see you. Hi.
Hi. So my question was about the autoencoders used. So did you ever experiment with different types of autoencoders for example, sentence-based parsing like charactergram encoders and word-based encoders, and did you find an advantage between the two?
Yeah. We have tried different ones, but we didn't see that big difference. On the contrary, the difference that we observed was when we spent more effort on schema linking. So right now in the system that we have a sophisticated value linking component, and that makes a lot of difference because, it doesn't matter what type of LLM you're using. These are always, get better and better. But the bet for us is to be accurate on one hand, and on the other hand, to use the LLM or the neural networks in general as only when needed, because they are very expensive. So, for example, these days we see approaches that use LLMs for all the parts of the architecture that we have seen. For example, they call the LLM to do the schema linking. So they will do several calls to the LLM just for the schema linking. Then they would use later a lot of calls to the LLM to use to do self-correction. But if you add up all this time, and we have submitted a paper on that in a conference in VLDB, to VLDB, you get extremely big times, big response times. This is the most important part.
Thank you.
Here you go.
Yeah.
One more question is coming up.
So hi. So my
Hi.
question is that working with the LLMs, there's a large situational bias when we extract information and especially converting it into something like SQL queries. I mean, it's really interesting, but I want to know, how do you handle eliminating the bias, and like, is this particular infrastructure viable for larger corpus of data sets as well?
Give me an example of bias, because there are
Uh,
different forms of biases. Give me an example.
Yeah, so like, for example, you are taking a string of words and you are using lemmatization. So one particular LLM might have a trend of lemmatizing it in a particular way,
Yeah.
but the context awareness of that particular type of conversion might not fit into a scope of one particular data type. So I just want to know, like, are you working or did you work on something to tackle this?
Yes, I understand what you're saying. There are different ways. I will tell you what we have tried. One way to try to tackle this is to fine-tune your model based on your domain, in order to try to make it more to make it to bring it closer to the data that you have. So that was one, and the other one. So pretty much, and I pretty much that was the one that worked for us, to be honest. But there are also other types of biases that may come, but we don't see them for the domains that we are working on. For example, now that we are building a BI tool for a big company that is using NL, we saw a different type of bias. I use quotes here, and we decided to switch from text to SQL, essentially, to text to code. Because the LLM would exhibit specific types of, again, I'm using bias in quotes, when we used the SQL, but we didn't see the same problems when when translating to code. For example, it would try to simplify the SQL query, but we didn't want the simplification. For example, ignoring that it should have included 2 joins, but because it was trained and it had seen many, simple examples, it would just say, okay, you have A, B, and C. I will connect them like this. This is the most obvious way, but we didn't want this. Switching to code, for code, it has, it translates each step as a separate, it translates code as a series of steps, and for some reason, it would not make the same mistake.
That's nice.
That's very interesting.
The black box of the black magic of LLMs.
Yeah, but if you think about it, there's way more training data for code than it is for SQL queries. So,
Exactly.
Therefore the quality has too much, right? So, although the database people in the room and you are like, oh my God, we are losing all that independence, all the nice stuff that we like about databases, but comes up with wrong answers.
Yeah.
Or any other questions?
Thank you very
So
much.
thank you very much,
I
Georgia.
have-
Thank you
I
very
have a
much.
question if you will.
Vangelis? Oh, no, Stephen.
Oh,
Hi.
I'm not sure who has a question.
Clapping or question?
He was clapping, was clapping.
Who is clapping? How about I stop
Yeah, I was
recording? If you have
clapping,
a
but
question, Vangeli, let's stop recording. If people,
Hello. Can you hear? Yeah, I think that would be
Yeah,
good.
yeah.
Yeah, I think Stephen had a question. He did